Hello everyone, in this lecture we'll be continuing our discussion about counting techniques that we use in the probability theory. So we will have two main points. The first point is review on the counting techniques, and then we will have a set of examples on those counting techniques. First of all, one of the main counting techniques is the multiplication rule. The multiplication rule states that if an operation can be performed in n1 ways, and then for each one of these n1 ways, a second operation can be performed in n2 ways, then the two operations can be performed together in n1 times n2 ways, hence the name multiplication rule. An example for that is that in a communication event, two symbols are transmitted in sequence. Each symbol is selected from a set of m symbols. Note here that he says that each symbol is selected from a set of m symbols. So as if we have a pool of m symbols and we can select any of them for transmission at a time. Which means that during the transmission of the first symbol, we have m symbols to choose from, and during the transmission of the second symbol, we also have m symbols to choose from. So for transmitting the first m symbol, we have m ways or m possibilities for that first symbol, and then for each of those m ways, the second symbol has one of m options or has one of m possibilities. So we have for each of the first m possibilities, we have for the second symbol m possibilities, and hence the total number of possible sequences to be transmitted is m times m or m squared. In the case, the wording is slightly different, where it says that we have an exact set of m symbols and we want or we select two of those symbols, or we take two of those symbols, then for the first procedure, for the first symbol to be chosen, we have m choices. However, once one of those m symbols is chosen, then the remaining set of symbols is m minus 1. So selecting or choosing the second symbol has only m minus 1 ways to select. So we have to be careful about the wording of the problem, whether that set is fixed and each time we select one of them we still have the whole fixed set of symbols like m symbols in this example, or this set of symbols is affected each time one of the symbols is taken out. We can then generalize this multiplication rule into what we call a generalized multiplication rule, which states that if an operation can be performed in n1 ways, and then for each of these operations, a second operation can be performed in n2 ways, and then for each of the first two operations, the first and second operation, a third operation can be performed in n3 ways, and so on. Then, generalizing the previous rule, we can say that the whole set of procedures can be performed in a number of ways equals to n1 times n2 times n3 and so on. So a simple example for that, if we have a menu, a set of 4 types of soups, 3 types of sandwiches, 5 types of desserts, and 4 types of drinks, how many meals can be formed from this menu? If I go to that restaurant and I order a meal which includes one of each of these 4 items, so how many meals can be formed, or what is the possibility of forming the number of possibilities of forming such meals? So here I can choose any one of the 4 soup types. Again, here we are not talking about a set of 4 fixed dishes of soups that we will take one of them and then we are left with 3 remaining dishes. No, we have a fixed number of possible types of soups equals to 4. So we can select one of 4 soups. So we have 4 ways to perform such selection, and therefore for each of those selections we can choose any of the 3 sandwiches or the 3 sandwich types that are available in that menu. So that's times 3. And then for each of the selected possibilities of the soups and the selected possibilities of the sandwiches, we have 5 ways to choose one of the desserts, and finally 1 of 4 ways to choose one of the drinks. So whatever number we get there, this is the number of meals that can be formed from this set menu. Next, let's go to the definition of permutation. Permutation is an arrangement of all or part of a set of objects. So we better understand this through an example. So let's assume that we have 3 receiver modules, A, B, C. Let's assume in general that we have a system that is composed of 3 subsystems, subsystem A, subsystem B, and subsystem C. And assuming that any possible arrangement of such systems will perform the required task or the required function of the overall system, a receiver in this way, in this example. So how many permutations can be performed? Even without the terminology of permutation, we can think of how many ways we can order or arrange these objects. So now let's assume that we have 3 positions, the first position, the second position, and the third position. And let's count the number of possibilities to fill the first position. So for filling the first position, we have 3 choices, module A, module B, and module C. So we have 3 choices. And then for filling the second position, now we have a reduced set size. So now if we select one of the 3 modules to be in the first place, then we are left with only 2 remaining modules. So for the second place or for the second order, we have only 2 choices. So here we have 2 choices, and again applying the multiplication rule, so far we have 3 times 2 possibilities. And then for the third place, we will be left with only 1 choice or 1 remaining module. So only 1 way can be found to fill such a position. So we have a total of 3 times 2 times 1 ways to fill the 3 places with the 3 modules. So this is what we call permutation. So again, permutation is an arrangement of all or part of a set of objects. In this example, it's an example on arranging all set of objects. As we gave an example before, let's assume that we have a classroom of 30 chairs, and then we have 30 students to fill those 30 chairs. So for the first student, he has 30 chairs available, so there are 30 ways to achieve that procedure, one student sitting on one of those 30 chairs. And then for the second student, only 29 chairs are available. So for the second procedure, only 29 options or 29 possibilities are there. Then for the third student, only 28 chairs are available, and so on till the last student, which will be left with only 1 chair available. Then applying the generalized multiplication rule, we have 30 times 29 times 28 and so on till times 1. So this gets us to the theorem which says that the number of permutations of n distinct objects is n factorial, and as we know, n factorial is n times n minus 1 times n minus 2 and so forth until 1. So here we have to be careful with the term n distinct objects. So we are talking about n objects which are different from each other. So in this example, we have 3 different modules, module A, module B, and module C. In the example of 30 students who will be using 30 chairs, we are talking about 30 different students. If those 30 students were exactly alike, were teddy bears or any other objects that are not distinct, or there is no way to differentiate between each of the 30 objects, then the permutation does not apply, or the n factorial does not apply, because any arrangement of those exactly alike objects over the 30 chairs will be the same. So actually in such scenario we'll have only one possibility to arrange 30 identical objects over 30 chairs. So again, to calculate a permutation or to use the n factorial rule, we have to make sure that the objects are distinct objects. So this is what we call permutation of all of a set of objects. Now we can even generalize it more when we have a permutation of n distinct objects taken r at a time. So let's assume that we have n objects and we are looking for how many ways are there to choose r of those n objects. In this case, this is what we call permutation n p sub r, and we calculate it as n factorial divided by n minus r factorial. So let's think of it through the example of 30 chairs, but in this next example we will have only 5 students. So 30 chairs or 30 places, 5 students. So how many ways can these 5 students sit on the 30 chairs? So again, applying the generalized multiplication rule, for the first student he has 30 options, the second student has 29 options, the third student has only 28 options left, and so forth. The fourth student has 27 chairs left, and the last student has 26 chairs left. So this is the number of possible ways 5 distinct students can be seated on 30 chairs, and we calculated it using the generalized multiplication rule. Let's check if the permutation theorem here, or the definition of permutation, still holds. So if we have npr, in this example that will be 30, from which we choose permutation of 5. So according to the rule, that is 30 factorial over n minus r, which is in this case 25 factorial. So again, by definition, 30 factorial is the recursive multiplication of 30 times 30 minus 1 times 30 minus 2. So that's 30 times 29 times 28 and so forth until 1. And 25 factorial is 25 times 24 and so forth until 1. So as we can guess, the product of 25 times 24 times 23 and so on can be cancelled with the similar part from the numerator, and we are left with only these 5 numbers multiplied by each other. So again, the permutations, it's only an application for the generalized multiplication rule. Let's take another example. So let's assume that we have 20 contestants in a competition, and in such competition we will have only 2 winners. So in how many ways can we find those 2 winners? So again, this is exactly similar to the example where we have 30 chairs and 5 students, but now we have 20 places, 20 students, 20 objects, from which only 2 will be winners, or from which only 2 will be selected. So the number of ways this can be done is 20 permutation 2, or 2 selected from 20. Again, here we have to be very careful in using the permutation. Will it be applicable in such an example or not? Yes, it will be applicable, because to choose 2 winners, those 2 winners will be different from each other. So we have from 20 participants, we will use 2 different winners. Okay, and let's consider the next example where we have 5 possible dates, and for those 5 possible dates we want 3 speakers to select 3 of those possible dates. So again, here we have 3 different speakers, speaker A, speaker B, speaker C, and we have 5 different dates. So we want choose 3 of those 5 dates. So choosing 3 of those 5 dates will be the first task. However, assigning each of those dates to one of the speakers, this is what makes those dates distinct from each other. So let's have it, let's put it in simpler words. Let's assume that we have date 1, date 2, date 3, date 4, and date 5. So the first speaker has 5 dates to choose from, so we have 5 possibilities, and then the second speaker has 4 dates to choose from, and finally the third speaker has remaining 3 dates to choose from. So the number of ways 3 speakers can be invited to speak in 5 possible dates will be 5 times 4 times 3. Here, in calculating the permutations, the arrangement of the objects makes a difference, and each different arrangement counts as one distinct way to achieve the requirement, or in this example represent one different way or one distinct way for such permutations. The permutation theorem can be then generalized more, so that if we want to calculate the number of distinct permutations of n distinct options, but now instead of chosen r at a time, now we have it of those n objects, n1 are of one kind, n1 objects are of one kind, n2 are of a second kind, and so on, nk are of a kth kind. In this case, the number of distinct permutations is calculated as n factorial divided by n factorial times n2 factorial, and so on. So if we go back to the previous expression, we calculated npr as n factorial divided by n minus r factorial, because we were selecting only r from general n objects. Now if we have those n objects are divided into k groups, that's the first group, second, third, kth group, and each group has n1 objects, n2 objects, n3 objects, and so forth. So the number of distinct permutations to have such arrangement is n factorial divided by n1 factorial times n2 factorial, and so on till nk factorial. For example, if we have different sets of decorations where we have, for example, 3 red decorating balls, 4 yellow decorating balls, and 2 blue decorating balls, that's a total of 9 decorations, and we want to put those decorations in 9 different places, then the number of ways to achieve this will be 9 factorial divided by 3 factorial, 4 factorial times 2 factorial. From this permutation rule, we can deduce what we call the partitioning rule, where if we have if we want to calculate the number of ways of partitioning a set of n objects into R cells, where those R cells include n1, n2, n3, and so forth, nr elements in each of those cells, then the number of such ways of partitioning is calculated as n factorial divided by n1 factorial, n2 factorial, and so forth till nr factorial. So for example, let's assume that we have 7 students that need to be assigned in 1 triple room and 2 double rooms. So we have 1 room that can take 3 students and 2 other rooms each can take 2 students. So how can we assign the 7 students to those rooms? Again, now in this example we have 3 distinct rooms. So here is the distinction or the notion of having 3 different cells or R different cells in general, and we want to assign from the set of n distinct objects. Here those are the 7 students. We want to assign each one of them to one of the 3 rooms. So we have 7 factorial divided by 3 factorial times n factorial times n factorial. Finally, this leads us to the very well-known combination rule, which says that the number of combinations of n distinct objects taken are at a time. This is now a special case of the previous case. So in the previous case we had n objects divided into r cells. Now as if we have only 2 cells, and by default if one of the 2 cells includes a number of objects, so the other cell will include the remaining objects. So we will have the total number of ways to achieve this is n factorial divided by r factorial times n minus r factorial. So this is what we call a combination of r objects chosen from n objects. So sometimes we refer it to, or we use the symbol NCR, or sometimes we use the binomial expression or the binomial notation as written here and as we used in the previous definition. So what is the difference between calculating permutations of R object chosen from n distinct objects versus choosing from n distinct options R combinations? The main difference is that when we calculate the number of permutations, the order of the chosen permutation makes a difference. For example, if we have a set of 3 letters A, B, C versus a set of the same set of letters but with a different arrangement like ACB, these represent 2 different permutations, because in calculating the permutations the order is important. So it's true that we have the same 3 letters A, B and C, but for the first permutations they are arranged in one way different from the way they are arranged in the second way. However, for the combinations, ABC and ACB are considered the same combination, because when we consider combinations or when we talk about combinations, that will be without any regard for the order of the elements. So we are looking for a set of 3 letters, irrespective those 3 letters how they are ordered. So the order is irrelevant, and hence we calculate the combinations, or we consider that these 2 arrangements are one combination. So they are 2 different permutations, but they are one single combination. That's why if we noticed, this equivalence of, or this way of calculating the combination is equivalent to NPR. Again, NPR was defined as n factorial divided by n minus r factorial. So NCR will be NPR divided by r factorial. So the number of combinations is usually less than the number of permutations. Again, because a number of permutations count as a single combination because the order does not make any difference. So let's try to understand this more through an example. Let's assume that we have 4 engineers and 3 technicians, and we want to find the number of teams that can be formed of 2 engineers and 1 technician. Note that here that we have 4 different engineers, 3 different technicians, and we want to form a team which is formed of, or which is composed of 2 engineers and 1 technician. So how many different teams can be formed? So out of those 4 engineers, how many ways are there to choose 2 engineers? And out of those 3 technicians, how many ways are there to choose 1 technician? For the second part, it's so easy. To choose 1 technician out of 3, there are 3 different ways to choose 1 technician from 3 technicians. Now for the first part, how many ways are there to choose 2 engineers out of 4 engineers? So the confusion here will be, is it calculated as 4P2, permutation of 2 engineers out of 4, or 4C2, the combination of 2 engineers out of 4? So which one of these will be the correct answer? It depends on whether the arrangement will make difference or not. So will it be any different if the team includes engineer 1 and engineer 2 compared to the case where the team includes engineer 2 and engineer 1? It doesn't matter. There is no order here. So a combination of engineer 1 and engineer 2 is similar exactly to a combination of engineer 2 and engineer 1. So the order does not make any difference, and hence we don't need to use the permutation. So the correct answer here is that there are 4C2 ways to choose 2 engineers out of 4 engineers. Now let's go back to the multiplication rule. Now we have 4C2 ways to choose 2 engineers out of 4 engineers, and for each of those ways we have 3 ways to choose 1 technician out of 3 technicians. So the overall number of ways to form the required team is 4C2 times 3. And if we want to apply this rule of calculating 4C2, so that will be 4 factorial divided by r factorial, which is 2 in this case, and by coincidence n minus r, 4 minus 2 is also 2 factorial times that 3. Finally, before we go to a more detailed set of examples, let's review the axioms of probability and some basic rules of probability. So in the probability theory, there are 3 axioms from which all probability laws can be derived. So axioms means that these are facts. They are logical results observed without any need for proof or any need for justification. They just make sense, and they are facts that can be accepted without proof. The first of these axioms is that the probability of an event, which we denote as probability of event A, this probability should be larger than or equal 1 and larger than or equal 0 or less than or equal 1. So the probability is the likelihood of an event. So definitely it cannot be a negative value. It makes no sense. It has no meaning. It might be 0 if that event can never happen, or if that event includes no elements with regard to the overall sample space. So the probability of any event should be a positive quantity. So that's being larger than 0. And the highest value of such a probability is that it is 100% certain. It is 100% possible, and that it is for sure will occur. In this case, the highest probability is equal to 1. And what is the event whose probability is equal to 1? It is the event which is identically the sample space. So we know that the sample space is the set of all the possible outcomes of a random experiment. So the probability of the sample space is 1, which means that if we run an experiment, so we are 100% sure that one of the elements of the sample space will occur. That's why we know, or we can say that the probability of the sample space is equal to 1. For any other event, if we recall the definition of an event, it is a subset of the sample space. So an event might be less likely to occur compared to the sample set. So the probability of an event is less than or equal 1. So this is the first axiom. We have already discussed this axiom while we are explaining the first one. It is that the probability of the sample space is equal to 1. Finally, for the third axiom, if we have two events which are disjoint, as we said before, disjoint means mutually exclusive, which means that if one of them happens, the other can never happen. So these are mutually exclusive events, and their intersection is phi. So the probability, the intersection of event A and event B is equal to phi. So the third axiom says that if two events are disjoint, hence achieve this condition, then the probability of their union, the probability that A occurs or B occurs, is probability of A plus probability of B, and this is what we can refer to the addition rule, is that if we have two distinct experiments and we want to count the number of ways these two experiments can be done all together, so we have a number of ways, the number of ways of the first experiment added to the number of ways the second experiment can be performed. And hence, if we want to calculate the probability of a certain event union another one, that will be the summation of the probability of occurrence of these two events. But again, this direct sum is only true if the two events are mutually exclusive and they are disjoint events. From these axioms, we can derive some important basic rules. For example, if we want to calculate the probability of the complementary event of A. So as we said before, A complementary, the complementary of an event is the complementary of the event with respect to the sample space. So that is all the elements in the sample space that are not included in event A. So the probability of the complementary of an event A will be the probability that the sample set occurs, excluded from it the probability that event A occurs. So, and as we said from the first axiom, from the second axiom, that the probability of S is equal to 1, then the probability of a complementary event is 1 minus the probability of the event itself. Next, if we want to calculate the probability of a union of two events, but for general events, now again remember, for the third axiom we calculated the probability of union of two events, but that was in a very special case where A and B are mutually exclusive or disjoint events. For the general case, for any two events A and B, the probability of A union B is the probability of A plus the probability of B. But while calculating these probabilities, we calculated the probability of the intersection twice, because the intersection of event A and event B is part of A and part of B. So if we draw such two events using Venn diagrams for explanation, let's assume that this is event A and this is event B, and this whole area is their union. So if we want to calculate the probability of that union, so that is the probability of an element being in such area. So when we calculate the probability of A, it is the probability of any element in such a space, and the probability of B is the probability of any element in such a space. And as we can see, we counted the elements in the intersection twice. That's why we have to exclude it once. So we end up with the rule that the probability of A union B is equal to the probability of A plus probability of B minus probability of A intersection B. Again, this rule has no conflict with the third axiom, because if the two events are mutually exclusive, then their intersection is equal to phi, and the probability of that intersection is equal to 0, then we subtract 0, and we end up with the rules that we have said in the third axiom. Now let's move to a set of examples on the counting techniques and calculating the probabilities to make sure that we can use the rules that we mentioned about counting techniques correctly in examples. Let's start first with very simple examples. So the first of those examples is that we have 9 professors who are to give talks in a certain conference. Each one will give only one talk. However, 3 of them are French, 2 of them are American, and 4 of them are Egyptian. So now we have 9 professors divided as 3 of certain nationality, 2 of a certain nationality, and 4 of a certain nationality. So again, this reminds us of the case where we have a set of n objects, 3 of them are of a kind, 2 of them are of a kind, and 4 of them are of a kind. And here he asks how many ways can their talks be scheduled such that professors of the same nationality follow each other. So now we want to arrange the 9 talks such that the French have successive talks, the Americans have successive talks, and the same for the 4 Egyptians. So as if we have divided the 9 professors into 3 groups now. So let's have a group of 4 Egyptians, and we have a group of 3 French, and we have a group of 2 American. So in how many ways can these be arranged? Under the condition that professors of the same nationality follow each other. That's why I grouped them this way. So we have here 2 aspects that we have to consider. The first of them, how will we arrange the 3 nationalities? Will we start with the Egyptians, followed by the French, followed by the Americans, or we will have another arrangement? So now, as if we have a number of sets, 3 sets, that we want to decide how are we gonna arrange these sets. So this is exactly equivalent to the simple example where when we said we have a number of dates and we want to assign people to those dates. Now we have 3 sets of dates and we want to assign 3 groups to these 3 sets of dates. So we can even start with the Egyptians. For the first set of dates we have 1 of 3 options, so we have 3 possibilities, and for the second set we have either of the remaining 2 sets of professors, so we have 2 possibilities, and finally we have 1 possibility for the remaining set of dates. So here we reached the solution of the first part of the problem using the generalized multiplication rule. If we want to use the permutations rule, so that is directly 3 factorial, because we are in need to arrange 3 sets of people onto 3 dates. So this is how or this is the part where we assign people to sets of dates. So let's assume that one way is that we will start with the Egyptians, followed by the French, followed by the American. So for this example, for this specific arrangement of the 3 factorial arrangements, how are we going to arrange the 4 professors who are Egyptians, and how many ways, in how many ways are we going to arrange the 3 French professors, and in how many ways are we going to arrange the 2 American professors? Again, we want to count these ways because they make difference. We have 4 different Egyptian professors, so arranging them in one way counts as a different way compared to arranging them in a different way. So let's assume we have Professor E1, E2, E3, and E4. Are we going to start with E1 or E2 or E3 or E4? So we have 4 possible ways, and then followed by one of the remaining 3 professors, and then followed by one of the remaining 2 professors, followed by one of the remaining professor, which is only 1. So we have 4 factorial ways to arrange the 4 Egyptian professors. Similarly, we have 3 factorial ways to arrange the 3 French professors, and 2 factorial ways to arrange the American professors. Again, this is for each of the ways we arrange the Egyptians. These are independent of the ways we arrange the French. So for each of the possible arrangements of the Egyptians, we have all the 3 factorial possible ways to arrange the French. So that is generalized multiplication rule, and this is all multiplied by the 3 factorials, the 3 factorial which refers to arranging the set of professors on its own. So again, to have full understanding of this arrangement, let's assume that we have the professors, the American professors, as A1 and A2. So how many ways can they be arranged? They can be arranged either A1 followed by A2 or A2 followed by A1. So these are 2 different permutations. They are 2 different arrangements because A1 and A2 are different from each other, and the problem dictates that starting with Professor A1 is different from starting with Professor A2. The same for if we want to arrange the 3 sets of professors, so we can start with the Egyptians followed by the French followed by the Americans, or start with the Egyptians followed by the American, finally with the French, or start with Americans, Egyptians, French, American, French, Egyptians, and the last 2 where we start with the French, then followed by the Americans, then Egyptians, or Egyptians, and finally American. So these are the 6 ways which are equivalent to 3 factorial here. Let's go to the next example. We have a dice which is tossed 3 times, and we want to find the probability of obtaining distinct faces. So for the 3 tosses of the dice, we can get 111, 112, 113, 114, up to 116, then 121, 122, 123, until 126, and so on. So let's first start with calculating the size of the sample space. Let's write first a few possibilities of the sample space. So 111, or 112, or and so on until 666. As we can see, the number of possibilities here is large to list, so we want to calculate them, or we want to count them using one of the counting techniques. So now we have 3 tosses. For each toss we have one of 6 possible outcomes, so we have a total number of ways equal to 6 times 6 times 6, so that is 6 times 3. Again, this is multiplication rule, and in this specific example, for the first toss we have 6 possibilities. For the second toss we still have the same 6 possibilities, and for the third toss we still have 6 possibilities. However, he didn't ask about the number of possibilities. He asked about the probability of obtaining certain event. So if this is the size of S, we want first to calculate the size of the event. So if we focus on the event of concern where we have distinct phases. So distinct phases means the 3 outcomes of the 3 tosses are different from each other. So for example, that is 1, and if we get the first toss 1, or if we select one of those outcomes and we get the one which starts with 1, so we cannot have 1 again here. So the second phase must be 2 or 3 or 5 or up till 6. And if you consider the first 2 outcomes, or the phases of the first 2 tosses are 1 and 2, then the third one can definitely be anything other than 1 or 2, for example 4, and so on. So again, now we want to count the number of outcomes or number of events in A. So in how many ways can we obtain distinct phases? One can mistakenly think that let's count the number of cases which we have the same phases and then subtract them from that total number. Okay, this is a very good way of thinking. However, do not do the mistake and consider that the possible cases of having similar numbers are 6, where we have 3 1s, 3 2s, 3 4s, 3 5s, and 3 6, because there are other cases where we have, for example, 1 1 and 3. Here we have 2 similar phases, so this again should be excluded from the event that we are focusing on. Now again, we want to calculate the probability of obtaining distinct phases, so the 3 phases should be different from each other. So we have to consider the cases where the 3 phases are identical and the cases where only 2 phases are identical. So what do you think will be the number of phases that need to be number of possibilities of having distinct phases? And once we get that number, what will be the probability of such event? The probability of such event, let's assume that this number will be x. The probability of such event will be the number of possibilities of this event divided by the total number of possibilities, the total number of having 3 phases in general, which is 6 power 3 as we calculated earlier. So this will be left as an example for you to think of a way to calculate or to find the number of ways to obtain distinct phases, and that will be our x. However, the needed answer will be finding the probability of such event, in which you have to divide that number of possibilities that you will find divided by the overall number of possibilities of having 3 phases in general, which is 6 power 3. Another example, here he says determine the probability of an even number or a prime number appearing in the toss of a fair dice. Here we have a direct application to the union rule, because he says that he wants to calculate the probability of an even number, having an even number, or a prime number. So let's assume that we have event A, and it includes the set of even numbers. So these are 2, 4, 6. Again, we are talking about tossing a fair dice. Fair dice means that the probability of any of the 6 phases is 1 over 6. Back to the second event. Event B is the probability of having a prime number. So these are 2, 3, 4 is not a prime number, 5, 6 is not a prime number. And we want to determine the probability of an even number, so that's event A, or event B. Again, as we said before, or is equivalent to the union, so we want to calculate the probability of A union B. There are two ways to solve such a problem. The first is to apply the rules that we derived from the axioms of probability. That's probability of A union B equals probability of A plus probability of B minus probability of the intersection. So what is the probability of A? The probability of A is the number of events in A, which is 3, divided by the number of events in the sample space, which is 6, so that's half. And the probability of B calculated same way, so that's also 3 over 6, which is half. And the intersection, if we want to calculate the intersection, so A intersection B is the set of common elements in A and B, so that's only the 2. So the probability of such event is equal to number of elements in the event, which is 1 in this case, divided by the total number of elements in the sample space, 1 over 6. Let's substitute, so that's half plus half minus 1 over 6, so that is 5 over 6. The other way to calculate it is to find the union set first and then calculate the number of elements in that set. So A union B equals the set of elements in A or B or both of them. So that will be 2, 3, 4, 5, and 6. So the probability of such event is the number of elements in this event, which is 5 in this case, divided by the total number of elements in the sample space, which is 6. So this is just a simple example to show us that there are more than a single way to find the required, and also it's an example to show us a direct application for this rule that we derived from the axioms of probability. Another example, let's calculate. Let's read it together. It says that the thickness of a copper wire is uniformly distributed over the interval of 1 to 3 millimeters. So we have a copper wire, and its thickness is somewhere between 1 millimeter and 3 millimeters, and all the possible thicknesses are equally likely. This is what we knew from reading that the thickness is uniformly distributed. Then he asks what is the probability that the thickness of randomly selected piece of wire is between 2 and 2.5 millimeters. So what if we consider that our sample space is the thickness of a wire, so what are the possible elements of the sample space? We know that 1 is a possibility, 1 millimeter is a possibility, 3 millimeter is a possibility, but between 1 and 3 we have infinite number of possibilities, because that is a thickness which can be any real number, 1.1, 1.2, 1.11, 1.19, and so on. So this is a set which has an infinite number of elements. So when we get to calculating the probability of a certain event, we cannot just simply count the number of elements, because that will be infinite. Even here, if we assume that event A, which specifies that the thickness is between 2 and 2.5 millimeters, so we have 2 is an element, 2.5 is an element. However, in between we have infinite number of elements, so we cannot simply calculate the probability of event A as the number of elements in event A divided by the number of elements in the sample space. Instead, we can divide the range of event A divided by the range of event of the sample space. That depends on the meaning of the problem. So here we have thicknesses or length, so we can calculate the probability as length divided by length. If the problem has the meaning of area, so we can calculate the probability as area divided by an area, and so on. If we have a problem whose meaning depends on volumes. So in this example, the probability of event A is the range A, which is 2.5 minus 2, divided by the overall range, which is 3 minus 1. So that's 0.5 divided by 2, which is 1/4. Let's go to the next example. A password is in a certain computer system consists exactly of 5 distinct lowercase letters. So how many possible passwords are there? We have only lowercase letters as our pool of characters, and the password consists exactly of 5 letters, and those letters are distinct from each other. So how many passwords can be formed in under these conditions? Let's think of it together. Yes, exactly. So we have 26 letters, from which we want to choose 5 letters. So these are 5 distinct letters. Will the order make difference here? It was not specified explicitly in the problem, but will the order make any difference here? Definitely it will make a difference, because we are talking about a computer system password. So one password of 5 letters is different from another password composed of the same 5 letters but with different combination. So the number of possible ways here will be calculated as permutations or combinations. It will be calculated as permutations. So this is the overall number of possible passwords that can be composed under this condition, is that our pool is the lowercase letters from A to Z, and that the password is composed of 5 distinct letters. However, he is not asking about that number directly. He is asking about the probability that a hacker succeeds in guessing your password. So the probability of such success is the probability of getting the exact password. So in how many ways there is an exact password, so that is just one way, and the probability of guessing such password is the number of ways the password is true, which is 1, divided by the overall number of passwords, which is 26p5. Note that this example is similar to the example that we mentioned earlier, and you should have thought about its answer, about tossing the dice 3 times, and we were hoping for 3 distinct faces. So what is the number of possibilities of having 3 distinct faces out of 6? So that's 6 from which we choose 3. However, will the order of those 3 make difference? Is 1, then 2, then 3 count the same as 3, then 2, then 1? No, they are 2 different permutations. They are 2 different possibilities. So we calculate the number of possible ways to have 3 distinct faces out of 6 as 6p3. So again, this is, go back to the example of tossing the dice 3 times. Next example, we have a printed circuit board which has 8 different locations, 8 different positions, 8 different holes in which a component can be placed. If 5 components are to be placed on boards, how many different designs are possible? So again, the question here, do we have, or are those 5 components similar or different? If they are identical components, if those components are identical, then how many ways are there to put these 5 components in the 5 different locations? Again, this is the same example as 30 students and 30 chairs and 5 students versus 30 chairs and 5 teddy bears. So if the components are identical, then from those 8 locations we want to choose 5 of them, but the order doesn't matter. So we have 8 from which 5 are chosen in combination. If the 5 components are different, similar to the example where we had a receiver with 3 different modules, so again we choose 5 from 8, but again in this case each permutation is different, or each arrangement is different, so we calculated through permutations. Another example, we have an 8-bit code word which is selected at random. So 8-bit code word, that means that we have a single byte, and as we know, byte is composed of 8 bits, and each bit can be either 0 or 1. So how many possible code words can we have out of 8 bits? So for each of the 8 locations, or for each of the 8 bits, we have 2 possibilities. So we have 2 times 2 times 2 times 2 for the 8 positions, so that's 2 power 8. So this is the total number of code words that can have 8 bits.
I didn't understand that.
But it is asking about what is the probability that it contains at least 3 0 bits. So one way of solving this problem is to list all the possible code words. However, that will be a large number. 2 power 8 is not a small number to list all the possible combinations, and it might become even more difficult if those are not bits, if those are, for example, decimal digits or so, in which case we will have 10 power 8 possible numbers. So we have to use one of the counting techniques instead of listing the possibilities. So we want to find in how many ways can we have at least 3 zeros. And we have to be very cautious here, because we are talking about having at least 3 zeros, which means we might have 3 zeros, 4 zeros, 5 zeros, or up to 8 zeros. So we have to count all the possibilities of having 3 zeros, all the possibilities of having 4 zeros, all the possibilities of having 5 zeros, and so on. So that will be a lot of cases to count, even with using the counting techniques. Instead, we can use one of the rules derived from the axioms of probability, such that we can count the remaining, or the complementary, the elements of the complementary events, and then exclude them from the total number of elements. Or in other words, we can calculate the probability of the complementary event and then subtract that from 1 to get the probability of the required event. Here the complementary event is easier to calculate and easier to find, because it will include a less number of elements. The complementary event here is having less than 3 zeros in the code word. So again, the event is that the code word contains at least 3 bits, so that's 3 bits or more, so the complementary event is having less than 3 zeros, so that's including only no zeros, 1 0 or 2 zeros. So what is the number of possible ways to have no zeros in a code word composed of 8 bits? So that is, from those 8, 0 of them will have zeros, so that is 8C0, and as we know, anything C0 is equal to 1, and it makes sense because there is only one way to have no zeros in a code word, in this case when we have 8 successive ones. How many ways can we have 1 0? So that 1 0 can be either the first bit, the second bit, the third bit, or the 8th bit, so that is 8, or again following the general systematic approach, that is 8 from which we choose 1, and the 8 possibilities are different from each other because the position of the 0 differs. Finally, to have 2 zeros in a code word, so that will be 8 from which we choose 2. However, again, the question here, is it 8B2 or 8C2? So we want to choose 2 positions for the zeros, but will it make a difference if the first 0 is in the first position or in the second position? Actually no, the 2 zeros are exactly identical, so we want to calculate combinations. Okay, so that's again exactly similar to the previous example when we calculated the probability or the number of ways to have 5 identical components in 8 locations. We calculated it as 8C2, so that is 8C2. So this is the total number of ways when we add them. Do we add them or multiply them? No, these are not events that for each one of them there is another possibility. Those are completely different ways. So we want to count how many different ways can we have no zeros, and how many ways we can have 1 0, and how many ways can we have 2 zeros. So we add these numbers, and the probability of such event will be the probability of having less than 3 zeros will be 1 plus 8 plus 8C2 divided by the total number of code words, which is 2 power 8. But don't forget, this is the probability of the complementary event. So what is the probability of the event itself? It will be 1 minus this number. So again, here we used many rules. We used the combinations to calculate these numbers. We used the permutations to calculate the overall numbers, and we used the axiom of probability or the rules of probability to finally get the probability of the required event. Our last example will be a similar example where we have a bin of 50 manufactured parts that contains 3 defective items. So we have a pool of 50 components, 3 from them are defective, and the remaining, that will be 47, are good items. Then a sample of size 6 is selected at random. So out of these 50 parts, we select 6. So before we continue reading, in how many ways can we select 6 parts out of 50 parts? Again, here the parts are in general identical to each other, so we have 50C6 to select those 6 parts. Now let's continue. What will be he asking about? He asked about the probability that the sample contains exactly 2 defective parts. So that means that out of these 6 we have 2 defective parts, and then by default the other 4 parts will be 4 good parts. So he is asking about the probability that those 6 samples includes 2 defective and 4 good. What are the possibilities, or what are the what is the number of ways this can happen? The number of ways this can happen is that out of these 3 defective we choose 2, and out of these 47 good we choose 4, and the number of possibilities that these 2 cases happen is their multiplication. So we have a number of possibilities as 47 combination 4. So this is the number of ways to choose 4 out of the 47 good ones, and for each one of those ways we have a number of possibilities 3 from which we choose 2, and their order does not matter. So this is the total number of ways to choose to have such a sample which has 2 defective items and 4 good items. If we want to calculate the probability of such event, then we have to divide this number of possibilities divided by this total number of possibilities of having any sample of 6 out of the 50 manufactured parts. So again, we use the counting techniques to count the number of samples in a certain event, or the number of outcomes in a certain event, and then we use the rules of probability. The general concept of probability is that the probability of an event is the number of elements in such event divided by the overall number of elements, and with the help of the axioms of probability and rules derived from these axioms, we can calculate the probabilities of more complex events like the intersection of events, the union of events, and complementary events.